All right, this video is from Chapter 3, Section 5, and our topic is equation solving and modeling. What you'll learn about in this video are solving exponential equations, solving logarithmic equations, orders of magnitude and logarithmic models, Newton's law of cooling. We will not be covering logarithmic reexpression. And why we're going to learn these things. The Richter scale, pH, and Newton's law of cooling are among the most important uses of logarithmic and exponential functions. These two functions have what we call one-to-one properties. What this means is, for any exponential function f of x equals b to the x, if b to the u equals b to the v, then u must equal v. And for any logarithmic function f of x equals log base b of x, if log base b of u equals log base b of v, then u must equal v. So let's use these one-to-one properties to look at solving some equations. Go ahead and pause the video right now and try to solve this equation for x. And so here's our solution for how to solve for x. Here's our original problem. And anytime we're solving with an exponential, our goal should be to try to isolate the exponential on one side of the equation, or we're going to try to get the variable out of the exponent. So the first thing we would do is to divide both sides by 40. And that would give us 1/8 on the right side of the equation. And then what we have to do is we have to be a little creative here. On the left side we have a base of 1/2. What we want to do in order to use the one-to-one property is we want to try to re-express 1/8. And what we do is we re-express 1/8 as a fraction 1/2 to the third power. And the reason we want to do that is because if you notice, once we do that, we have exponential expressions on each side of the equation, both with base 1/2. And once we have that set up, we can use our one-to-one property to take the exponents of the two and set them equal to each other. So x over 2 equals 3, which is a very simple solve, x equals 6. An example of this with our logs, go ahead and try to solve log of x cubed equals 3. So log x cubed equals 3. Okay, here we're trying to use our one-to-one properties. So what we're going to do is we need to have logs on both sides. We only have log on one side. And so you'll see here we have log of 10 cubed. So the question is, how do we go from 3 to log 10 cubed? Well, again, we have to be a little creative, and a lot of times our creativity involves the number 1. The number 1 can be expressed many different ways. But one way that 1 can be expressed is log 10. And we looked at this property a couple lessons ago, but log base 10 of 10 has a value of 1. So when we take the value 3 and we multiply it by log 10, that still has a value of 3. So we can multiply this 3 by log 10, and we don't really change the equation at all. We don't change its value at all. It's still equivalent. But what we can do, once we have a log here and we have this 3 times the log 10, we can take that and rewrite that as log 10 cubed, which is how we get this here. And the reason that's so important is because now we have log over here, log here. We can use our one-to-one property to make this a much simpler equation. X cubed equals 10 cubed, and if x cubed equals 10 cubed, then x must equal 10. All right, so we need to be able to solve logarithmic equations a little more advanced here. So we're going to use maybe our one-to-one properties that we just looked at. We may have to use some of the properties that we've looked at in past lessons. So here's a logarithmic equation. Go ahead and solve this equation on paper, and we're going to look at two different ways to solve this. We're going to first look at how we use our graphing calculator to do this, and then we'll talk about how we do this algebraically. Alright, so here's how we're going to solve this using our calculator. A little typo there. So we're going to use the x-intercept method, calculating zeros. And what we have to do is we first have to get all the terms on one side, 0 on the other side. This is in function form. So we're going to say, all right, let some function f be all these terms. And we're just going to type that into our calculator. We're going to use our 0 tool, and we're going to find the x-intercept, and that is 1/2. That is the solution to this equation. All right, very simple. We have to be able to do this by hand though. Calculator's nice, you can use it as a tool to check your work, but we're going to need to be able to do these by hand on paper. So what we do is, here's our starting equation, and what we're going to do is, the first thing we're going to do is our goal is to get to where we have one natural log on each side of the equation. If we can get to that point, then we can use our one-to-one property. But to go from here to here, we have to know how to do that. And since we have two natural logs being added together, we can use our product property to rewrite these two natural logs that are a sum as a product of 1. So we have the natural log of the quantity 2x plus 1 times the quantity x plus 3. And that equals this natural log over here. Once we get to this point, we use our one-to-one property, and we just solve these. And this becomes a quadratic situation. And so we use our quadratic solving tools, and we come up with two solutions, x equals 1/2, x equals -5. Now we know from the graphing calculator that x equals 1/2 is our solution. So the question is, why isn't this one a solution? It is an extraneous solution. And anytime we're solving equations and we get these two solutions, we always need to check for extraneous solutions. Now, our original equation here has natural logs in it. And so extraneous solutions, remember, are solutions that don't make sense in the context of the original problem. The original problem has natural logs in it, so we have to consider what makes the natural log of x undefined. Well, x cannot be less than or equal to 0. Okay, so the domain of the natural log function is positive values. Now, x is negative, and that's not the problem. The problem becomes when we substitute -5 in any of these expressions. If any of these turn out to be negative, then we have to throw -5 out. It is possible that -5 could work in these expressions. If these expressions all were set up so that when we substitute in -5 and simplify these, we get positive values, -5 could work. But in this case, you see here, this is going to be a value of -9, and this one here would be a value of -2. So here we have two cases where the solution -5 does not work, because the natural log function is not defined for negative values. So we have to check for extraneous solutions. Another application of logarithms is the Richter scale, used to measure earthquakes. The Richter scale magnitude, capital R, of an earthquake is given with this formula here, where A, little a, is the amplitude in micrometers, or micrometers, of the vertical ground motion at the receiving station. Capital T is the period of the associated seismic wave in seconds, and capital B accounts for the weakening of the seismic wave with increasing distance from the epicenter of the earthquake. So right now we don't need to understand the science behind this equation or formula at all, but we would need to be able to take some different values and substitute them into the equation and solve for an unknown value. So this is just an application. Another application involves pH. In chemistry, the acidity of a water-based solution is measured by the concentration of hydrogen ions in the solution. That's in moles per liter. The hydrogen ion concentration is written H+. The measure of acidity used is pH, which is the opposite of the common log of the hydrogen ion concentration. pH equals negative log of H+. More acidic solutions have higher hydrogen ion concentration and lower pH values. So a third application here is Newton's law of cooling. An object that has been heated will cool to the temperature of the medium in which it is placed, meaning if you put an hot object in cool water, the medium would be the water. If you pour a cup of hot coffee and set the cup out on the table, the medium would be the air temperature. The temperature T of the object at time little t can be modeled by capital T of little t equals T sub m plus the quantity T0 minus Tm times e to the negative kt. For an appropriate value of k, where T sub m is the temperature of the surrounding medium, T0 is the original temperature of the object, And this model assumes that the surrounding medium maintains a constant temperature. So there cannot be, if you think about taking a hot object and putting it in cool water, we're assuming that the cool water is going to remain the same temperature. And remember, T naught, we've seen this a few times now, T sub 0, that's what we call an initial condition, initial value. It's going to be a common thing, common occurrence in many applications all throughout pre-calculus and calculus courses. So here's an example using Newton's law of cooling. A hard-boiled egg at temperature 100 degrees Celsius is placed in 15 degrees Celsius water to cool. 5 minutes later, the temperature of the egg is 55 degrees Celsius. When will the egg be 25 degrees Celsius? So we've got some information here. We have an equation in the previous slide that we can use. So take a few moments, pause the video, and see if you can come up with a solution to this problem. So this problem seems like it should be a fairly straightforward calculation of a time value, but we have to think a little bit about how we attack this problem. We're given 3 pieces of information. So if we take those pieces of information and our equation that models the situation and put the values in, we have a function value of 55. We have a medium temperature, the water, of 15 degrees. We have a difference of the temperature of the object, the egg, okay, minus the temperature of the medium. That's where the 85 comes from, 100 minus 15. And then we have a time value of 5. So we don't know K. Okay, and K is not the time that we're looking for here. So what we have to do in this problem actually is take a situation that we're given, solve for this K value, and then after we know the K value, turn around and use the information that we have for the problem that we're actually trying to solve, and then use the same equation to solve the equation for the situation that we have, that we're trying to figure out. Okay? So we're given information about the egg after 5 minutes. We're going to use that information to find K, and then we'll go back and find the time when the egg is 25 degrees. So we substitute our values in, solve for K, right? As you can see, we're trying to isolate the exponential here, and then at that point it becomes a matter of taking the natural log of both sides and then solving for K. K has a value of 0.1507. So we take that K value and we substitute it into the formula. We substitute 25 in for the temperature. We substitute our initial conditions, our values that we know, and now we're solving for T. And so the process is very similar as it was over here. We're going to use the natural log, and we find that T is 14.2 minutes. So after 14.2 minutes, we can expect the egg to be 25 degrees Celsius under the given conditions. Now, if the given conditions were different, then the answer would turn out to be different. But based on these conditions, initial conditions, this is the time that we would expect the egg to be 25 degrees Celsius.